Hello, everybody. So I'm Haseeb. I'm a managing partner at Dragonfly, which is a global crypto investment firm. And I'm talking to you guys today about the intersection of crypto and AI. So this is a sector that's gotten very hot lately. A lot of people are talking about it. And as an investor, I see a lot of pitches from a lot of different startups that are trying to build something at the intersection of crypto and AI. So this talk is going to be a bit of an overview to look at all the different things people are building and why they're building them. So first of all, why crypto and AI? You can't see this. All right, whatever. Why crypto and AI? They're both sectors that have a lot of bullshit. But the one thing that's nice about crypto and AI is that crypto is an industry that creates trust, and AI is an industry that is in sore need of trust. And so there are very many interesting intersections where the two of them can empower each other. So let me give you an overview of the different areas where people are building smart contract networks or decentralized networks in the intersection of crypto and AI. First is decentralized compute. This is basically GPU marketplaces, because of course GPUs are what you use to train AI models. And right now there's a massive GPU shortage around the world. Part of the reason why NVIDIA is such a valuable company is that they're building most of these really valuable GPUs that everyone wants for machine learning. If you can't get those GPUs normally, maybe you can get them through a decentralized marketplace at a cheaper cost than through Amazon or one of these centralized cloud providers. So the two big networks here are Render and Akash. Render, about 5 billion fully diluted valuation. Akash, a little bit under $1 billion. The second category, so first you've got the GPUs. You get the GPUs from a decentralized marketplace. Now you need to train a model. Okay? So decentralized training, there are a few different startups that are working on this, but this is a very hard sector to get right because training is extremely expensive. We heard earlier in the previous talk, some companies are paying millions of dollars on these training runs. So it's very difficult to do this completely in a decentralized way. But if you look at BitTensor, which today is the largest AI token, about $12 billion FTV, it works more or less in decentralized training. You can sort of think of it as a decentralized Kaggle, where it's a competition to train a model that has maximum performance on some particular objective function. There's also Jensen, which is a pre-launch startup that is also doing decentralized training. The third category is inference. And this is what I'm going to be diving deep into in this talk. Okay, so inference is, you've got the GPUs, you train the model, now you want to run the model. But you don't have the ability to run the model yourself. You're going to use a decentralized network to run the model for you. Okay? So Ritual, Modulus, there are many different startups. This is probably the most common pitch that I see as a VC is people working on decentralized inference. So just very quickly to go through how a machine learning model works. If you don't understand that, it's useful to get some context of what's going on. When you train a model, first you have a lot of data, and ideally data that's labeled. Okay, so this is a car, this is a person, this is a strawberry. And once you have all these labeled data, use that to train the model, and anytime your model makes a mistake, you update the model weights. These are all the parameters of the model, or sort of the neurons in the model. You're updating them using backpropagation and gradient descent. And you do that over and over and over again for all these different things. And here's where you're paying the millions of dollars. Right? You're doing gigantic training runs with many, many terabytes of data that you are training this model with. Okay? Then once you have the trained model, and the trained model is very big, and it costs a lot of money to get it. But once you have it, then you can run inference, which is you give it a picture, you say, what is this? And the model will do all of its magic, and it'll say, oh, this is a bicycle. Okay? That part is much cheaper than the training. But it's still non-trivial to actually get good inference and fast inference and consistent inference on a model that you have. So to be clear, there are other AI projects in crypto that are more application layer, like MyShell, which is chatbots, Kaito, which is doing data analysis or looking at trading metrics. But I'm going to be focused purely on the decentralized inference protocols. Okay, these are purely decentralized protocols. So let's look at why this is a problem. Okay, let's say that you want to run a very popular model like Llama 270B, which is made by Facebook. Llama 270B requires 140 gigabytes of RAM. Most people don't have 140 gigabytes of RAM, right? Even if you have a GPU at home, it probably doesn't have that much memory. So in order to run a model like this, you need someone else to run it for you who has a beefier computer than you have. So now, you might not want to trust a centralized provider like Mr. Sam and his company. And so if you choose not to do that, you might think, okay, well, I want to do this, but I need to be able to trust the output. Right? If I say, great, I'm going to run Llama 70B, but how do you know if you're doing a decentralized network that you're actually getting Llama 70B? You might be getting Llama 7B. Someone might be lying to you and then actually running a cheaper model than the one you asked for. So anytime you're doing this in a decentralized network, you have to assume someone's cheating you. So how do you make sure you don't get cheated? Well, the answer is you need some kind of verification. How do you verify this was the model that you're running? So you could think, well, that's why we have blockchains. We have smart contracts. So put the machine learning model in a smart contract, run the smart contract, done. Right? Okay, this does not work. The reason why this does not work is it's way too expensive. Okay? GPT-3 has a hidden layer. The embedding size is 12,288 parameters. Okay? 12,288 weights. A single matrix multiplication of this size would cost $10 billion in gas on Ethereum today. It would fill every single block for a month straight, just one single matrix multiplication. Okay? So, and there's thousands and thousands and thousands of these in a single machine learning inference. This is not going to work. All right? So we have to find some way to do this off-chain more efficiently than running it all on the blockchain. All right? So there's a continuum of 3 different approaches that people are taking of how to build decentralized inference. The first is what's called ZK-ML. So you've probably heard of ZK, zero knowledge proofs. These are kind of cryptography, moon magic, in order to prove very efficiently that somebody did this computation. Okay? Now the problem with ZK-ML is that it's very slow. It takes a very long time to generate a proof over a machine learning model the size of Llama 270B. It's very costly, so there's probably a factor of about 1,000x of the cost of naive inference doing a zero knowledge proof over that inference, and oftentimes even more depending on the architecture of the model. And it's slow as hell. It's about 1,000 times slower than what you'd otherwise have to do running a normal model. But the advantage is that it's extremely secure. If I run a ZK proof over any model, you know beyond a shadow of a doubt you ran the machine learning model just like you said you would. And you can also do privacy if you so choose. There's other fancy stuff you can do with ZK, but mostly this is for just pure verification. So this is insanely expensive. There are some projects that are doing this, like Ezekiel, Giza, Modulus, but right now it's not very practical to do on large models. Okay? Then on the other side, you've got crypto economics. Okay? Crypto economics is more or less what you think of when you think about blockchain consensus. So this is proof of stake, everyone kind of votes. I think that the output is this. I think the output is this. And we all have stake and we vote and we see if you're different from everyone else, you get slashed. That's crypto economics, right? So it's not particularly fancy. It doesn't really use any of the unique aspects of AI. It just sort of treats it as any other crypto economics problem. If Chainlink were doing machine learning, this is probably what they would do. They would do something like this. So Ritual, Atoma, these are all networks that are doing the crypto economic approach. And the advantage of crypto economics is that it's fast, it's cheap, it's mostly secure, right? Depends on how much stake is there, what's your incentive for cheating me. But it's pretty easy. It's pretty easy to get it up and running and to get something that's relatively secure using crypto economics. So ZK, you're paying a factor of 1,000. With crypto economics, how much are you paying in order to do an inference? Well, in crypto economics, all of the nodes that are running consensus, they all have to also run the computation. So if I say, predict whether this thing is a bicycle, all the nodes in consensus have to also run the same model to see whether they agree that it's a bicycle using that model. And if let's say there are 20 nodes, then you have to pay 20 times the cost because you have to pay all those nodes to run that computation, right? So whatever is the number of nodes that will be doing the crypto economic voting, you got to pay all of them to do the underlying computation. The third approach is optimistic, and it's somewhere in between those two. Okay? So optimistic machine learning basically says, I'm going to assume that when somebody responds and says, oh, okay, yeah, that's a bicycle. I ran the model. It's a bicycle. What we're going to do is we're going to assume that that's correct. But if it's not correct, then somebody can submit a fraud proof to prove that this person didn't correctly run the model. Right? So it's very similar to what optimistic rollups do. You assume it's correct unless someone can prove that it's wrong. And you have to wait before you actually can confirm and say, yes, this thing is definitely a bicycle, because that person might have cheated, and you have to wait for the challenge period to expire. So this is using some kind of challenge response game akin to TrueBit. So it's the same thing that optimistic rollups do. So you start, I'm gonna run through this because we don't have a lot of time, but you basically play a verification game, okay? So these are more or less the 3 big mechanisms that I'm seeing today of how people are trying to build these decentralized inference networks. The thing that's interesting about them is that these are not new. These are actually very familiar mechanisms in order to determine whether a given computation is correct. So you can see, actually, if you go to the blockchain security continuum, much like the continuum I showed you of decentralized inference, what's on the ZK side? In normal blockchains, you've got ZK rollups, right? That's exactly what they do. They do the same thing as the decentralized inference guys are doing ZK, which is that they generate these ZK proofs that proves that the computation is correct. Starkware, ZK Sync These guys are doing exactly the same thing, just not in machine learning, right? Same thing, what's optimistic? Well, that's the optimistic rollups. Optimism, Arbitrum, they do the exact same thing with the fraud proofs. And then crypto economics, that's most layer ones, right? What do most layer ones do in order to determine that this computation, this transaction was executed correctly? They use crypto economics. So it's the exact same toolkit that we use in crypto, but adapted to machine learning, okay? Now, there is a lot of differences though. So when you're thinking about machine learning has unique challenges that blockchains don't have, okay? Now, what are these challenges? The first thing to think about, well, machine learning is just another computer program, right? At the end of the day, saying, okay, run llama 7db, and there are all these parameters and matrix multiplications, blah, blah, blah. At the end of the day, that's just a program. And what we do in blockchains is verify that programs are run correctly. So why is this different? What is actually different at all about doing this with machine learning versus any other program? Well, the first thing about machine learning is that machine learning is not designed to be proven. Machine learning is designed to be fast. It's designed to be fast on the architectures on which machine learning models are trained, okay? A normal machine learning model can be represented as a graph. So if you see this thing right here on the left, a graph basically means that there are all these computations that have to get done. All of those different weights are different multiplications that are happening. And they can happen in any order as long as the graph goes left to right, okay? So this graph, when a GPU is executing this graph, remember, GPU has thousands of cores. So they're executing this graph in a highly parallelized way, executing many different branches simultaneously and then collecting the results and moving forward, okay? In this super parallelized computation, it doesn't really matter which branch goes first, which one goes second. I don't really care. All I care is that I got all the way to the end as fast as possible, okay? That does not work if you're doing program verification. In program verification, you have to verify that these steps were followed in this order. And if you didn't follow this step in this order, then you have to go back and see, oh, okay, where did you get it wrong, right? So you need a linearization of what is not a linear computation. This linearization is expensive. It means that you have to take a machine learning model and compile it into another format that can then be proven. And if you compile it down into this linearized format, now it's actually less efficient to run it on a GPU, because GPUs take advantage of that parallelism. And if you unroll everything into one long linear computation, then the GPU is not going to be as effective at running that linearized computation. So that's one problem with all these decentralized inference networks, is they have to adapt the model into a system that makes it provable. Okay, the second thing that's a problem with decentralized inference is that, okay, let's say we've got all these different nodes. Let's say you're all nodes in the network, and you all run llama 70b to try to get the right answer about whether or not this thing, llama 70b is not a classifier, but let's say you run ImageNet and you try to see, is this thing a bicycle? Okay? Well, the thing is, even if all of you are running the same model, you may get a different output. Why would you get a different output for the same model? The answer is, not all GPUs do the same thing. So a different GPU architecture might result in a slight change in the output of some matrix multiplication or something like that. Or even having a different version of CUDA. Having a different version, like not updating your OS basically, may mean that you end up getting a different result, which is kind of bullshit. So the same model does not necessarily mean the same result. So you have to fix, everyone in your network has to use the exact same model and the exact same architecture to make sure that they're actually getting the same output. So if you try to say, give me a picture of Sam Bankman-Fried, two people who are running the same model might get a different result because of pure randomness inside the model. The third thing is that floating points are cursed. I don't have time to talk about this, but floating points are not associative, meaning that if you add two floating points or multiply two floating points in a different order, you can get a different output. And that output can cascade over the course of an entire model. So this means that even the way that the cores are executing, the order in which the cores are executing all these parallelized computations, they may be slightly different on each run, even within the same architecture, within the same GPU. And if that's true, you may get a slightly different output. For an LLM, it might not make a difference, but for a classifier or a generative image, you might get slightly different pixel values because the outputs are slightly different because of these cascading floating point errors. So if you want to do this, you either have to avoid using floating points, which sucks, which is super, super slow on modern GPUs, or you need to allow some laxity in outputs because there's so much non-determinism in GPUs that in order to get two GPUs to agree, you've got to allow a small amount of error. So these are all these different implementation details that don't show up in normal programming verification, right? So if I'm doing a smart contract on Ethereum, these are not problems. Ethereum doesn't even have floating points because Ethereum knows that floating points are fucking crazy and you should never use them for financial applications. But in GPUs, floating points are all what machine learning does. So This is why this is really hard. I don't have time to talk about this, but one new promising area that many people are exploring are TEEs, or Trusted Execution Environments. The very newest generation of NVIDIA GPUs come with trusted execution environments on the device, which means that now you can do confidential computing inside of an H100, a B200. These are only the highest end models. Most people don't have these. And they're still very, very new, so there's not a lot of people using them yet. But I think these will be a new promising area for the next generation of protocols to potentially use TEEs to get some kind of verifiability or even confidentiality for decentralized compute. So, takeaways. Crypto AI is big, it's early, and it's really hard. There are a lot of problems to be solved here. It's not guaranteed that any of this is going to work or be useful, but it's a very interesting area and one that I'd encourage you all to keep a close eye on. So, that's it. Thank you.